A step-by-step guide to solving a quantum Hamiltonian with eigenvalues and perturbation theory. Welcome everyone to a comprehensive walkthrough of solving a quantum Hamiltonian, including the exact solutions and a perturbation theory comparisons. Alright, so here in problem 7.12, we have quite a lot on our to-do list. Starting off with considering a quantum system with just three linearly independent states. That'll make the linear algebra fans happy. And suppose that the Hamiltonian in matrix form is given as such, where V0 is a constant and epsilon is some small number much less than 1. That'll become important when we look at the approximation schemes. So in part A, we wish to write down the eigenvectors and eigenvalues of the unperturbed Hamiltonian epsilon equals 0. Okay, that'll be nice. Part B, solve for the exact eigenvalues of H and expand each of them in terms of a power series in epsilon up to the second order. And that's where the epsilon being much less than 1 will come into play, and we'll see why that works out so nice. Part C, use first and second order non-degenerate perturbation theory to find the approximate eigenvalues for the state that grows out of the non-degenerate eigenvector of the unperturbed Hamiltonian, H0, and compare the exact results from part B. So what we see is that we have to make a big comparison from C to B and D to B, so keep those parts from B in mind when you're moving through this. And then in part D, use degenerate perturbation theory to find the first order correction to the two initially degenerate eigenvalues and compare the exact results. Okay, quite a lot to deal with, a whole lot of words and a whole lot of moving parts, so we will take our times in putting these pieces together in the self-referential way that this problem is structured. No big deal there. And this is why this problem is important. How do we handle a Hamiltonian that has non-degenerate and degenerate energies and their corrections? And we do this, of course, with linear algebra. Not so much in the integral sense as so much in the inner product sense. All right. So, challenge for you is, well, what we'll see is that we end up with the diagonal matrix here in the first part, but why are these matrices so nice? And why do we spend so much time trying to put matrices into diagonalized forms? If the form rings a bell, P, D, P inverse, that should ring a bell, and it has very nice properties for us to use, and overall, linear algebra comes into play more than we like it to. That being said, there are going to be a lot of steps in this that are left out in the video, so go ahead and check out the PDF in the link below. That's for you to follow along with, and it will be fun for us in exploring this theory and building up your notebook for the rest of quantum mechanics. And finally, if you find value in this content, you can have a direct impact on its success by liking, subscribing, sharing with a friend, or donating through Buy Me a Coffee. No account required. Now, on to the fun. Alright, so stop number one then. We have what we're tasked with doing is finding the unperturbed Hamiltonian eigenvalues, which, for the record, if we recall, this gave us H0, or the superscript rather, gave us the energy values of the original system, recalling again that the total Hamiltonian in this theory was the unperturbed with the perturbed. So keep that in mind because it plays a role throughout this whole thing. So the unperturbed, we just set that epsilon equal to 0 as given in the question, and we start chugging away. As you see, we plug in 0 here, and then we factor in V0 to every value or every entry into the matrix, and we see we get our lovely diagonal matrix. Now, one of the reasons why we love diagonal matrices is they tell us quite a bit. Every entry on the main diagonal is an eigenvalue. So our eigenvalues are V0, V0, and, oh, that should be a 2. Excuse me, I don't know why I have a 3 there. That should be a 2. That should be a 2 right there. So excuse the typo, but that should be a 2. Because that's what we see on the main diagonal. And then, moreover, what we see is that the eigenvalues are actually the reduced column vectors of this diagonal matrix. So if we factor this out or divide by V0 to everything, we see that we get, in this column, a 1, 0, 0, corresponding to eigenvector 1. In this column, we get a 0, 1, 1, or 0, 1, 0, vector 2. If we normalize that and get rid of that, we have a 0, 0, 1, which is our second or third eigenvalue. So that brings us up to our first checkpoint on. And again, we didn't have to use a characteristic equation. We were just able to use the niceness of diagonal matrices. And that's just one reason why we love them. There's plenty more, of course, especially with, well, yeah, you'll see the challenge. So try that out, but definitely realize diagonal matrices, they're your friend. All right, so with that, we can move on to stop number 2. Awesome. So what we're tasked with doing now is to re-visualize this Hamiltonian problem, being that the Hamiltonian, being the operator, gives us eigenvalues of E, so that's why we use it. Except now we have to find the exact solutions of this Hamiltonian with the unperturbed and the perturbed states. So to do that, we use the characteristic equation. And this again, you might want the PDF if you want all a little nitty-gritty work. But from here, we see that setting up the determinant, not bad at all. Because we have these lovely zeros here and zeros here, if we wish to use cofactor expansion along the first row, that's easy. If we want to use about the first column, that's easy too. Either way, you get a couple of zeros in the cofactors from these two terms here and here. So whatever they multiply as 0 saves us a lot of time and energy there. So choose wisely on your cofactor expansion row. But nonetheless, we see here that when we do that, this first cofactor right here multiplied by crisscross here, and we just get a polynomial equation. This is the characteristic equation. If we go ahead and distribute and simplify this curly bracket, we get a leading term here of lambda squared minus 3 v0 lambda, and then we have 2 minus epsilon squared times a v0, which that just comes from the last terms here, 1 v0 times 2 v0. That gives us 2 v0 squared, and then we have a v0 squared here. So we just factor that out, and we're good to go. All right, so with that, if both of these things equal, the cases that we need to solve for is for when the first bracket equals 0 and when the curly bracket equals 0, and that leads us to two separate equations. So let's go ahead and clean that up and get our eigenvalues. All right, clearly the first equation's easy. We just add that lambda over and we get lambda 1 equals v0 times 1 minus epsilon naught. Cool there, don't have to worry. Now for lambda 2 and 3, we have to use the quadratic equation, so just be careful in plugging things in. We see that the negative signs here cancel, beautiful. This negative 3v0 becomes positive 9v squared. Distributing this 4 times 1, which is just 4, into this gives us 8 minus 4 epsilon naught squared. But because we have a squared term here and a squared term here for the v0s, we can factor that out. Of course, 2 times 1 just gives us 2. No big deal. Algebra away. 9 minus 8 gives us the 1 here. And that v0 squared, after it's factored, can now come outside the square root at the reduction of power. So we're looking good now. And here's where they want us to expand this exact solution into the quadratic, from the radical into the polynomial form. And that's where we have to be careful. Because they tell us we want only up to the second order in epsilon. So expanding this square root here, as we see given there, we're good to go. Of course, we can factor out the v0 from both terms and the 2. That's right there. But all of these cancel out because they're higher order than the 2 that they want. So we're good there. This 1/2 reduces this 4 to the 2 we see here. And now we're good to go to set up our cases and summarize all the eigenvalues for part B. All right, fair enough, fair enough. So by looking at the top sign or the plus, we have 3 plus 1 plus 2 epsilon naught. Good to go there. Condenses down, factor out of 2, cancel, cancel. And then we're left with 2 plus epsilon naught, or epsilon squared, excuse me. And then lambda 3, we just use the minus signs. So after that, we distribute here and here. So with that, 3 minus 1 gives us 2. That negative 2 is there. Again, factor the 2 out. And then you see we're just left with 1 minus epsilon squared. Altogether then, we see that the exact solutions and the approximations for this Hamiltonian are given as such. Okay, so keep these in mind because we will have to come back to them when we're seeing the comparisons in part C and part D. So that does give us our lambda values for this Hamiltonian as a general. I'm just trying to make these distinct. These are not the eigenvalues for the perturbed Hamiltonian. They're just the second set of eigenvalues for the total Hamiltonian. So I really should have denoted that as a 0, but nonetheless, we see how it's playing out. That brings us to stop 3, which is part C. And if you don't remember, equation 7.4 told us that the total Hamiltonian was composed of the unperturbed and the perturbed Hamiltonian. Of course, we set that lambda factor equal to 1 if you're following along in the book. Not bad there. But since we're given a total Hamiltonian, we have to decompose this thing into its separate parts. So let's see how we can do that pretty quickly. All right. So if we look at this, what we were given is that everything in terms of the perturbation is going to be in purple. Everything in terms of the unperturbed is in blue. And we see that by putting appropriate zeros where they go, we see like right here, this was just an epsilon entry. So the unperturbed component was 0. And then we can continue doing that. Here we had a 1 on the main diagonal. So the perturbation term was 0. And so this helps you break it apart if you're not used to visualizing it. And then, of course, everything in the purple has an epsilon, so we factor that out. And now you see, consequently, the two parts of the Hamiltonian. And if you notice, this blue one was the exact one we found the eigenvalues of in the first part. And if you recall, linearity tells us that we can find the eigenvalues of the unperturbed and the perturbed and add those eigenvalues together, again, thanks to linearity, to find the total energies. And that's what we're using here. And we're comparing to those two additions to the exact solutions for the Hamiltonian as a whole. Okay, so that's the game plan here for this question. And now let's see how we can execute it. Of course, in the first order theory, what we're calling upon is equation 7.9, which is the expectation value of the perturbed Hamiltonian. Again, realizing that we already solved for the eigenvalues and therefore the energies of the unperturbed. Once we find this, we can add them together and be good to go. All right. So with that, we use equation 7.9 given here. The only thing really to note here is that as far as consistency and notation is concerned, these are not wave functions. These are state vectors given by the eigenvectors. So be aware that's what the notation transcends to when you start plugging things in. And if you don't remember how to deal with the eigenvectors in the case of the Bra-Ket notation, go revisit what 3.89 and 3.90 gave as definitions. And as we see, if we're the bra over here, we need the conjugate transpose to make sure the dimensionalities match. Linearity, of course, tells us that we can bring this constant outside. And now we're ready to do matrix multiplication, which if you forgot, you take this row and you multiply it into this column. That gives you one entry in the next matrix. So let's go ahead and continue this calculation and run it down. All right, so here is the multiplication of the perturbed Hamiltonian and the Ket vector. Here is the Bra vector written out, or in terms of its dual. The conjugate transpose, we don't have any imaginary units to input, so we're good. But we just need to transpose the dimensions, so that's what we have here. Row to column multiplication again leads to a 0. So we see that the first order correction is actually 0. That's kind of cool, but that's why we have to break it out to second order sometimes. And that's what we see in the next step. In order to find the second order correction to the non-degenerate eigenvalue of this Hamiltonian, which was the 2v0, right, we see that we have to use the states 3 right? Because that was the non-degenerate eigenvalue, and therefore tells you that m cannot equal 3 in this case. Okay, and then again, be aware that these are not wave functions but state vectors. Okay, so the reference case here is 3, highlighted in red, and we have to calculate this for the other two states of the system. And that was m equals 1 and m equals 2. Of course, with the eigenvector here and the eigenvector here, we saw that the unperturbed energy was 2v0. That was the only one that was non-degenerate, so we're good. We have Vm, Em, and then V3 with reference to the Hamiltonian that's perturbed. Let's plug in all our things now. And realizing that we only had two other states to consider for this Hamiltonian, hence m equals 1 and 2. So we're good there. Now we're just going to plug in and get everything right in terms of our ordering. So we have the summation of two things to deal with, V1, V2, E1, E2. So let's plug them in and calculate away. All right. So if the text gets a little too small here, definitely reference that PDF, which has it all in the same size, so you can follow along easy. Okay, no big deal there. The only thing else to note here is that we have to be very careful in putting in the correct order here. Again, the other states go on the left, so we have a conjugate transpose there, and the initial state was given as the reference state, so Vm, and we're good there. Of course, we saw that we could bring that E or the epsilon V naught outside of the inner product or the Dirac notation brackets, and we have to square that due to the formula. And so just be aware, trying to clean this up as you go. Of course, plugging in the energies, we saw that we got the unperturbed energy, so V naught and V naught, good to go there. And we see that that simplifies to V naught in the numerator, which cancels with one factor of the V naught in the numerator. Cancel, cancel. We like that. This right here, this matrix multiplication leads to a new vector. This matrix multiplication leads to a new vector. So it's easy enough to go that way. Now doing row to column here for this inner product. And then right here, we see that we get a 0 here, so 0 squared. It goes bye-bye. And then this gives us a factor of 1. So we get a second order correction of epsilon squared V naught. Now again, thanks to linearity, what we were able to do is separate out and solve for the unperturbed case, which is the E naught, and then the higher orders of the perturbation case. So that'd be E1 and E2 in this case. Again, because this energy was non-degenerate, we're allowed to use the non-degenerate theory, and this is what it leads to. The non-degenerate case plus the non-degenerate energy correction of the second order. And then, of course, the first order correction does not exist, so we're good to go there. And so we see that this is actually, once we factor out V naught, the same energy value that we saw from lambda 2 from part B. That's pretty cool, can't lie, pretty cool. All right, moving on to part C then, or part D, excuse me. That will be stop number 4, and this is where we deal with the other two degenerate eigenvalues of the unperturbed matrix. So with that, if we're going to move into this, we only know the tools for the first order degenerate theory right now. Of course, we can go ahead and use higher order if we need to. But what we see here is that equation 7.28 for the dually degenerate states is going to be used, and that's just taking the inner product again before we plug into the bigger equation, which will come later. But we have to find all the ways that this state vector interacts with itself and the other state. Okay, so that's the WAA here. AA being that this is V1 and V1. And of course, now we've seen how to deal with the inner products. We just take it, do some matrix multiplications, which computers love. So that'll help in higher order theories. And of course, whenever we multiply down, we get a factor of -1. So that just leaves us with a interaction, what we would say is an interaction correction of negative epsilon V naught. All right, and again, this is all to the first order. So we're good to go there. Let's go ahead and move on to the other interactions. We have interactions with B with itself. And then we see here, plugging into the same form, saving a little bit of space, we get that interaction leads to a 0. Cool, we could like that. That'll make our lives easier. And then here, we only need to calculate the interaction between A and B due to the fact that we could use our friend again in the fact that Wij is equal to W star Ji. And because these are all real values, we're good to go. And even if they weren't real values, using this thing makes it simpler than calculating another inner product. So feel free to utilize that in all of these problems because it definitely saves you time, and I'm all for doing that. Nonetheless, A, B, plug in the appropriate eigenvectors there, which is V1, V2, and let's calculate this down. All right, so here we get a 0, 0, 1 after that first multiplication. Row to column, we see that 1 times 0, 0 times 0, 0 times 1. They all add up to 0 here, so we get another 0 correction. And this is where we can use the first order energy corrections for the degenerate theory, which is given by equation 7.33. Okay, so if you go back and read the book, you see that gives us all the little necessary details. And this is a lot easier to deal with than we thought, where this was WAA, WBB, AA minus BB, and then the interaction term between the two. And we see that this being 0, that 0, that 0, it simplifies down so nice. Be aware that this negative epsilon V0 goes here. This being a square value gave us a epsilon squared V0 squared. The negative sign would cancel. So taking the square root of those squares led us to an epsilon V0. And then we could factor that out, of course. And now we see that we get our two states. It doesn't really matter what you call them. Just be mindful that the plus signs have to go to one value, the minus signs have to go to another value, so on and so forth. And that's what we see here. For the energy 1 correction that we have, just use the plus signs. Good to go. Not bad at all. You see that simplifies down quite nice because -1 plus 1 gives us a 0. So this correction term cancels. Again, this is only to the first order, so we don't have a second order approximation to deal with. But here, E2, we have the unperturbed and the first order perturbed. And with the minus signs, we get a negative here. So let's recall then that this is actually, E2 is actually the lambda 1 from part B to the first order. That's pretty cool. And of course, this is lambda 3. Lambda 3, can't seem to write today. Lambda 3 from B. So that's pretty cool as well, all to the first order. So that's a pretty nice thing to see. And it shows you again the importance of linearity in this theory. And it allows us to solve for these. So whether we just want the perturbation corrections, then we add them to what we are already given, which is something we pretty much already know. Or if we just want to find the exact values from the whole Hamiltonian, both are fine. But either way, what this problem does is show you the self-consistency of the linearity, breaking that Hamiltonian down into the unperturbed and perturbed parts, knowing that the unperturbed with the perturbed gives us the whole values to everything, and that's what part B showed us. Very cool. We like to see that. That should have been 1 and 2. I don't know why the 3's there. Making goofy typos today. My apologies. Whew, that was a hefty problem, but a fun one. And I'm glad that the author suggested that was a necessary problem. At this point, there's so many things to do as far as like understanding not only the application of the theory, but why the theory works. And so far, they have not suggested to do anything of showing why the theory works. So you might want to do that. In fact, I went and looked back at my course notes from when I took this years ago, and my professor made us deal with all the linear algebra headache of it. And I think that's why I like it so much, because it was something math intensive. So definitely look at those yourselves, and I might just post more of them on the Patreon so you can have access to those, because quite frankly, It's going to be the tool of your trade if you're going to be an experimentalist or even just a theorist. Perturbation theory is in every sector of physics, and the better you can have that theory understood, the more likely output you will to have successful understanding in the higher dimensional stuff that you deal with. So don't be afraid to go look at those because they are very nice to have. Um, that being said, I must give a massive thank you to all my supporters for making this possible. I'm extremely grateful for your support. And if you'd like to see more of this stuff, especially the theory side, you can also become a patron for access to the supplemental material, current and future projects, and one-on-one help. New content is posted weekly to fuel your curiosity. Books, notes, and other reference material are found below. If you have any questions, please feel free to reach out. As always, thank you for watching, and until next time, stay curious.